Hi, you're on a rock, floating in space, surrounded by more rocks and gas, and a bunch of nothing mainly. Oh hey, look at that, the rocks are going around the gas. Hold on, what the heck is going on here? To understand, let's look at a little bit of physics. Wait, did I say a little bit? To find out what kind of magic this is, we'll have to go back in time. Okay, not that far. Stop. Yeah, that's perfect. This is Gravity Guy, but most people call him Isaac Newton. One important thing he said is that force equals mass times acceleration. Now what do all these words even mean? Force is just a push or pull on something in a certain direction. Mass tells you how much of something there is, and it's also a measure of inertia, but we'll get to that later. And acceleration is the derivative of velocity with respect to time, but that's too many big words for my taste. So let's just say it's how fast velocity is changing. The key takeaway is that if you apply a force to a fixed mass, you get a predictable amount of acceleration. If you know all the forces acting on a basketball mid-air, you can predict with 100% certainty if the ball will go in the hoop or your neighbor's windshield. Whoa, did an apple just fall on my head? Yes, Newton, it did. That must have happened for a reason, said Newton, as he discovered that two masses attract one another, making the apple fall. Yes, even you, no matter how ugly you think you are, attract pretty much the whole universe, at least a little bit. Hey, can you put that on paper? Yup, said Newton, who gave us the law of universal gravitation. In other words, how much two bodies pull on each other given their mass and distance times a constant. Bigger mass, bigger pull, bigger distance, smaller pull. Actually, a lot smaller pull. You see, as the distance increases, the force gets smaller by the square. That, my friends, is the inverse square law. Gravity is also the reason why the planets in our solar system orbit the sun. They got their initial velocity when the solar system formed out of spinning gas, and since there's nothing in space to stop them from moving, they'll keep moving. Hey, that's Newton's first law. The sun is so massive that the force of gravity keeps pulling the planets toward the sun, but the planets are fast enough to essentially fall toward the sun but miss it, and this goes on forever, creating a round orbit. Actually, that's kind of a lie. Most orbits are not perfectly round but more egg-shaped, and Pluto's orbit is just a complete mess. But you get the idea. In this case, gravity is what we call a centripetal force. One thing many people confuse is mass and weight, and no, they are not the same. Mass tells you how much of this blob there is, and weight is the force of gravity the blob would feel. To make things clear, your mass would be the same on Earth and on the Moon, but the weight you would perceive is different because the Moon has a weaker gravitational pull, meaning a weaker force acting on your mass. So really, you're not overweight, you're just on the wrong planet. Alright, enough about Newton, let's break some stuff. If you ever dropped your phone, it might look like this. What the hell, ground, why'd you do that? The answer is energy, you know, the thing kids have after eating gummy bears. Energy has the unit joule. And it's not like force, it doesn't have a direction, it's just a number that's kind of chilling there as a property of a thing. You see, there are two main kinds of energy, kinetic energy and potential energy. In plain English, energy of movement and stored energy due to some circumstance. For example, when you held your phone, it stored gravitational potential energy due to being held above the ground at a certain height. Once you dropped it, the potential energy was converted into kinetic energy as the phone fell. Then it smashed into the ground, and the phone absorbed some of the energy, making the screen go boom. Work is defined as force applied over a distance. For example, if you lift an apple by 1 meter, you would have done about 1 joule of work. This happened by converting chemical energy stored in your body to gravitational potential energy stored in the apple. As you may have noticed, energy and work have the same unit joule. So they must be the same thing? No. Energy is the total amount of work that a thing could possibly do. Work is just the stuff that actually happened and required energy. You know, force applied over a distance, which most often implies converting energy from one form to another. If you try to lift a weight that's too heavy for you, you'd feel like that took a bunch of work, right? Well, yes, but your feelings are invalid in the face of physics. Mathematically, no work has been done, because work is a force applied over a distance. And since you didn't move the weight at all, no distance means no work. The key thing to remember about energy is that it cannot be created or destroyed, only converted, aka the conservation of energy. Okay, but a car that's moving has kinetic energy. When the car stops, assuming the car doesn't smash into a wall, where does that energy go? When you apply the brakes, there's friction between the brakes and the wheels, causing the car to slow down, and creating heat as a byproduct. That heat is then dissipated to the surrounding air, and that makes the molecules in the air move faster, and things that move have kinetic energy. So ultimately, the kinetic energy is transferred from the car to the air. With this knowledge, we can define that temperature is just the average kinetic energy of atoms in a system. You see, all atoms, not just molecules in the air, wiggle, like this. The faster they move, the hotter things get. That is temperature. All that talk about hot stuff, I think it's time we talk about thermodynamics. It tells us that jumping in lava is probably a bad idea, but more importantly, the absolute mess that is entropy. Literally, it tells you how much disorder there is in a system, indicating the number of possible states a system can be in. For example, get an ice cube. No, not that one. Yes, that's perfect, and put it in the sun. The sun will obliterate the ice cube and turn it into water. Looking at the structure of ice and water, we can see that ice is more neatly organized than water, which just kind of goes all over the place. Also, the water could look like this, or even this, but the ice will always look a little something like this. In total, the system went from low entropy to high entropy, meaning more disorder and more possible microstates. This trend applies to everything. The whole universe is on an unstoppable path to higher entropy. It's also the reason why time seems to go only forward, or at least that's what we believe at this point. Practically, entropy tells us that some forms of energy are more useful for doing work than others. Burn some gasoline and your car will move, spitting out heat and gas. That heat and gas are pretty much gasoline, just in the form of higher entropy. And as you can imagine, this stuff won't really make your car move, and the gas won't spontaneously turn back into liquid gasoline, meaning the form of gasoline with lower entropy is more useful for doing work. Okay, but if you put some water in the freezer, will it not decrease in entropy? Yes, but the fridge is not an isolated system and will heat up the room more than it will cool down the water, increasing the total entropy. Want to see some magic? Whoa, what just happened? Some electrons apparently moved through some wires and let there be light. What is going on here? Objects have a fancy something called a charge. It can be positive or negative, or if you have the same amount of both, an object is neutral. Electrons have a single negative charge. The flow of electrons is called electric current. To describe it, we use three parameters: current, voltage, and resistance. Current is the amount of electrons passing through a wire.